Good morning, everyone. Welcome in the second day of International Conference Use of R in Official Statistics, the 9th edition. We are very proud to welcome you. Today we have the second keynote speech of Mr. Edwin De Jonger from Statistics Netherlands. And I will give the floor to my colleague from Statistics Austria, Alexander KOWARIK, to introduce him. Thank you so much. Have a pleasant day together with us.
Yeah, good morning. Welcome also from my side. I have the pleasure to chair this keynote session, keynote presentation given by Edwin De Jonger. He's a methodologist and data scientist and at CBS. And many of you will know him by his work, so by his R packages. He has a list of, I don't know, 20 R packages, something in that ballpark, where he contributed or is currently the maintainer. Many of them are also on the awesome list for official statistics. The title of his keynote is The Unexpected Value of R in Official Statistics. So that's quite nice, and it might relate also a little bit to make a little advertisement for tomorrow to our discussion on computing in the statistical office. So that might be related a little bit. So his current research is data editing, complexity science. Very interesting topic about networks in business registers is listed as a research topic. That's a very cool figure. I wanted to do that myself, but we don't have the data for it, unfortunately, or I think we don't have it. So the keynote presentation will be about an hour, a little bit shorter because we should have time for questions. So maybe like 50 minutes, 55 minutes tops. And then we will have questions. Feel free to type in the questions already during the presentations. If Edwin answers the question in the remaining part of his presentation, we will manage to skip the question. So feel free to immediately enter the question so you don't forget the question. Yeah, with that, I will hand over to Edwin and look forward to a nice presentation by him. Please go ahead.
Thank you, Alexander. I'm very pleased and honored to give this keynote speech. So first I will share my screen. Start presentation. So the unexpected value of R in official statistics. So first of all, I've been an R user for some time. So I would like to start with a puzzling remark first. So in statistics production, most time and effort is spent in other activities than statistical analysis. Well, most of us do know this, but it's a bit puzzling, of course. And if you look at statistics education, it mostly deals with statistical analysis and methods, which is very fine, of course, but it's still puzzling that statistical production time and effort is not spent in analysis. So we all know that R excels in applying statistical methods in using them. Since we spend more time in doing other activities, does that limit R in any way? So that's a puzzling remark. I hope to answer some of these puzzling remarks. So who am I? I'm Edwin De Jonger, over 20 years at Statistics Netherlands, CBS, methodologist, data science, working a lot with R mainly, and as Alexander introduced me, I've done some methods in data visualization, data cleaning, and currently network analysis.
Görsen kulak alsana o.
Am I?
Yok, adamı gösterir dedi, ben kimim? 20 Niederlande
Excuse me, can you mute your microphone? And Anna, or Anna, can you mute the colleague? Thank you.
Sorry. So first of all, let's look at what official statistics are according to Wikipedia. So the first line of Wikipedia of tomorrow says, official statistics are statistics published by government agencies and other public bodies such as international organizations as a public good. So I have highlighted public good, well, because it introduces some extra demands on statistics. So the Wikipedia definition of official statistics sees the production of official statistics as a public good. So official statistics as public good means that statistics should be available for citizens, society and science, amongst others. Also that the methods must be documented. So how are these numbers of statistics produced? And production should be transparent and cost efficient because it's a public good and it should be as efficient and transparent and objective as possible. Well, that makes R and R packages a natural fit for producing official statistics because in R, all statistical methods and tools are open and documented, and using R scripts to produce statistics fits and fills these demands. Furthermore, to make it more cost efficient, R packages that are developed by official statistical offices can be shared between offices. Methods can be shared, making it more comparable, of course. So statistics should be comparable when the objective is to compare statistics, and it makes it also more efficient. So just using the definition as a public good, we can see that R can help with statistics, producing statistics. The other thing is, of course, these are statistics. These are statistics published by government agencies and other public bodies, such as international organizations as a public good. So let's look at the definitions. So when you look at statistics production, most time and effort is spent in these other activities than statistical analysis. So what other activities? Let's revise this puzzling remark. Well, again, Wikipedia, because people, that's the go-to definition database. Well, the first line in Wikipedia of today is on the topic of statistics. Statistics is the discipline that concerns the collection, organization, analysis, interpretation, and presentation of data. So that's not only analysis, it's collection, organization, interpretation, and presentation too. And these are exactly the things we're doing in our offices. So a large part of our activities are about collecting the data, organizing and improving the data, analyzing it, of course, interpreting it, and communicating it and presenting it. And all these aspects are quite important and take a lot of time. So let's So if you clam these two definitions together, so statistics available to citizens, society, and science, visual statistics can be described as statistics activities, plus making these available to the general public. Now, I'm stating this because if you look at R packages produced by official statistics, many are used to disseminate or publish statistics. It's actually quite a good thing, but I will come back to that later. So producing statistics is not enough. You also have to make them available and communicate them. Otherwise, they won't be used. And that's the main purpose of making official statistics, of course. So how does R support these official statistics? Well, let's have a look at two sources. some small statistics, very simple statistics. So let's look at the current task view of official statistics survey statistics. So many of you know that CRAN or CRAN has so-called task views. I'm not sure if everyone knows them, but on the website of the CRAN, so the public network collecting all R packages, there are also task views describing themes. One of them is on statistics and survey statistics. So I'm clicking on this right now. You can see that this is about many topics. So official statistics and survey statistics. The maintainer is Matthias, TEMPL, who is well known in our community, of course. And there are lots of topics and lots of packages. The other one is the awesome official statistics software. So I will, so first, just by a couple of people, including Alexander of Alex, who introduced me right now, and also Adrian and Mark van Loo. The awesome statistics software collects all software which is open and can be used by which is used in the production of official statistics. It's a list of all kinds of items. So let's do some small statistics. Actually, also official statistics software does do some statistics on it. There's a data directory containing packages in the page itself, and there is a visualization directory with some nice visualizations. Let's look at them now. So when you look at the current task view of the official statistics, you see many topics, and many are centered around survey design. So you can see that R was mainly used in the beginning surveys and doing visual inspection of data. So editing and visual inspection is also a very important aspect of official statistics. Interpretation, of course, statistical disclosure control, statistical adjustment and forecasting. So all these topics have their place in the statistical office. Many of them are on analyses, of course, but also on creating surveys, for example, so collecting data, organizing the data and improving the data, so imputation and editing, for example. Well, if we look at how many packages there are in this page, written in small R script, of course. So we can scrape this page and collect all the links in it. On these links we can create references and the names, and we filter on which are a package and which are no packages, because there are also some extra links, and we do it unique, and we get the number of packages, and the number of packages on the task view page is 101. So, which is quite a large number. So, and this excludes all kinds of packages which are normally used in R. So the packages like dplyr or data table or other packages are not on this page. So these are just packages which are quite relevant for applying or producing official statistics. So that's good to remember, that R has many packages just for producing official statistics. The other source is the awesome list, so the awesome of officialstatistics.org. So this visualization was made by Adrian. And the circles note how many packages there are in these different processes. So this page is organized using the GSBPM process, which is standard for labeling the processes within the statistical office. What you can see is that there are a couple on designing. Some packages on this awesome list are on designing these outputs, design variable description, frame and sample, collecting, and there are many packages on process. Also many on analyses, but the biggest one are on disseminating data. So there are lots of packages disseminating visual data, which is a good thing. You can also create a bar chart looking in these awesome lists, how many of them are R packages. And if you look at these, you can see that more than 70% of these packages listed in the awesome list are R packages. So this list is the list of open available software for producing official statistics, or which can help in producing official statistics, and a very large majority is written in R. So that's a good thing. It's good to remember. So R seems very useful for official statistics. So 72% of software is in R. This awesome list, of course, and many unexpected uses outside the realm of statistical estimation. You can find other arguments and practices in this document and Mark. So R gives us freedom to develop what we need as a statistical office, and brings in a wide array of applications. So not just statistical estimation, but also these other parts of the statistical process, including publication. And R helps in filling these gaps in the statistical process, as you can see from the previous visualization. And of course, we all know that, and we use it. That's because this conference is here. We use all these tools, such as data table and tidyverse or Markdown or Shiny. So I would like to illustrate unexpected uses of R in using my own examples. So R brought me in a couple of unexpected places. And amongst others, visual validation, data cleaning, of course, statistical disclosure control, and dashboards. So I would like to illustrate some of the uses of R in official statistics, using my own journey into R territory. So visual validation. This is a nice quote of John Tuckey. The main tasks of graphics are to reveal the unexpected and to make the complex easier to perceive, which is really a really good summarization of what visualization typically does. So it often shows what we don't expect, which is in contrast to what when we calculate a statistic, then we are we want to see the expected value, of course, but graphics help you to see the unexpected. So unexpected values can be revealed using visual validation. There are a couple of tools for that. So one of them is the table plot. So of my R journey, we looked into table plot, which is a visual summary of a large data set. It can be used to assess several quality aspects of distribution of large data sets. So I did this together with a couple of my colleagues, so Matthias and Das, and we published an article on it. But let's see what it does. So for table plot, to produce a table plot, the recipe is quite simple. So one takes a data set, preferably quite large, it is sorted on a numerical variable, for example, age. Chop the data set into 100 slices, and for each slice you calculate the frequency, if it's a categorical variable, or the mean, it's a numerical variable. And you plot these and you inspect. And of course you can enjoy the result. So how does this data set, how does this look like? Well, we didn't just experiment with it, we also applied it on a real use case. Let's see this use case. So the use case is the Dutch Census. In contrast to many other offices, of almost all national offices, Netherlands doesn't have a real census. So we have a virtual census. So since 1981, we don't have a real census anymore because the Dutch population found an intrusion to their privacy. It's a bit cynical, of course, because, or ironic, because nowadays they publish everything on the web, of course. But still, we don't have a real census anymore. So we compile it with population registers and all kinds of registers. So we combine population register and education register and employment registers to create a data set which is similar to a real census. But of course, this combination of these registers needs some checking. So there can be missings or kinds of errors and failures in the data set. The data is about 17 million persons, because that's the number of inhabitants in the Netherlands. So what you can do, you can create this graph with it. So this was created using R, and it's a table plot. So the recipe of the table plot is that you sort on one variable. So with the age, it's the first column. The next columns are age group, gender, civil status, if you're a child in a household or not, household size, level of education, and the last one is socio-economic category, so if you're working or not. Red, by the way, so the red color is used for missing values. So what you can see over here is these are the, because it's sorted on the age category, and these age groups are then chopped into 100 pieces. So each percentile is sorted on age. And you can see that the population starts at, the young population is 50-50 in male and female, and at the end, when people are old, there are less males and more females in the population. Green is unmarried, this is married, this is divorced, and this is widowed. So you can see the structure of the civil status. But most importantly is that this visualization was done on a raw, so a very preliminary combination of three different data sets. So it was the population register in combination with education register and the employment register. What you can see is that we saw some small glitches in the data. So we had a couple of very young people, so babies, having registered no missing education. It's easy to fix because they couldn't have any education. But you can see that for the older population, lots of records are missing, so there's lots of missing data, so correct for that. The same is true for the employment register or the social economic status category. For these red categories, we don't know what social activity or what economic activity they employ, so to find out and do some extra surveys in that. So here you see that just using a visualization tool with R you can summarize and analyze a data set without doing any real statistical analysis. So that's one thing of one usage, looking at visually looking at data. Large part of my work in R is on data cleaning. And R is specifically fit for that because R can be used as a domain-specific language. Data validation, but also for all kinds of other stuff. And we sort of know that. So NSIs, or all statistical offices, spend a lot of time fixing their data. So when you collect data, there's no such thing as good data. All data is flawed. So what you have to do is check the quality of the data, remove errors or outliers because there's no data without errors or outliers, correcting or adjusting data. So data can be corrected, and of course imputing missing data. So often you have to impute data that is missing. And R helps in making this process reproducible and transparent. There are lots of packages on data cleaning. Many packages can be defined. So for example, Vim is very useful in visual inspection for missing values and determining whether your missing values are selective or not, random or not. Mice is a very nice package in using an advanced notation method, imputing multiple values for missing values, so it's more statistically sound. There's a nice package called Sympop, which collects all kinds of methods which can be found in other packages, provides a nice interface for it to support notation. Datamate is a package which can be very useful in determining the quality of your data set. So it applies all kinds of summaries on your data set. And there are a couple of packages where I was co-author of, I'm a co-author of Validate Tools, Error Locate, and DC Modify, which apply all kinds of methods for trying to validate or improve the quality of the data. These methods and the underlying theory of that is in our book, Statistical Data Cleaning with Applications in R. So if you want to look into the theory of that, feel free to buy the book. So we created a couple of packages, so including Validate DB, Validate Tools, Error Locate. So the Validate and Validate DB are on validating data, checking the quality of data, and creating reports on what the quality of the data is. Error Locate is in locating specific errors and determining what fields or what values are wrong. Validate Suggest is creating new rules, and DC Modify and DC Modify DB are on creating correction rules. So if there's some peculiarity in the data, create a deterministic rule to fix that rule, fix that data. And all these packages have the same underlying principle. So that's only for these packages, not for the other packages which I mentioned. These packages all have the same underlying principle, namely rules. So we use R to specify rules in these data cleaning packages. And describing these rules makes it predictable and deterministic, and also more controllable, which helps in our mission to create statistics which are transparent and can be reproducible. So in these packages, we use R syntax to specify a rule, and we store, annotate, and document the rules. And when new data arrives, we evaluate and execute the rules in context of data. Or in our lingo or our jargon, we confront the data with the rules. So let's an example of that later on. And we can do this because R is a very powerful language underneath. I'm not sure if it's well known to you or to, I know many of you do know this, but it's not known to every R user, but R is a really powerful language. In R, all language constructs are so-called expressions. So in computer science expressions. And R is a so-called homoeconomic language. It can interpret, modify, create, and evaluate its own expressions. So you can create within R statements which can be evaluated with R. So it sounds a bit like a Gödel thing, but you can create statements and in R, or you can create expressions in R and modify them and re-evaluate them, which is really powerful. So for example, a language like Python doesn't have this ability. It's not built into the language. Right? Just a couple of languages which can do this. So for example, Lisp is very famous for doing this. The language Julia is also able to do this, but it's not as advanced as R is in the evaluation part. It's advanced in the expression part, but not in the evaluation part. So R's evaluation is very powerful. When you have an expression, you can evaluate it into any R environment, so of your choice. And this sounds a bit abstract, but we will look into this later on. And this feature is used by many key R packages. So maybe you didn't think of it, but formulas in R are really expressions. So when you specify R y tilde x, this is an expression. And when you use it in linear regression, for example, this expression is evaluated in the context of the data frame. So you use the data frame in which variable y is available and in which the variable x is available, and this expression is then evaluated within the context of this data frame, which is really powerful. In Python, for example, you can do this. You have to specify this with strings or something, or use the column names itself, but not this way. So formulas are using this. In plot and ggplot, this is also used to specify data mappings and titles. So when you do a plotting in R, plotting and ggplot use the expressions of the variables you put in, and they use it to label, for example, the axes, or to make a mapping between a variable in the data frame and the plotting device. And of course, the data manipulation packages use it a lot. So for example, data table, we try to derive a new variable or to do selections within the data table itself. So this, So this is a child column which is added in data table syntax, and it's added because apparently the data table contains a column called age, and this expression is evaluated in the context of the data frame. The same is true for dplyr. So we do a mutate on the data frame and same statement. This is evaluated in the context of the data frame. TEMPL. So this feature is used quite a lot, and it's a very nice feature for analysts. So when working with the data, it's very nice that you can use these statements or these variables, which are names of the actual columns of your dataset. R also contains a couple of functions which are not that well known to manipulate these expressions. So for example, quote, substitute, and bquote. Bquote is not very well known, but it's a really nice function. So these are used to create expressions, quote, substitute, and bquote, and evaluate is used to evaluate the expression, so to turn it into a value. There's also an extra package called rlang, which does something similar and which is used by the tidyverse. So all these packages use expressions internally, so use a key feature of R. So one of the things we do in validate, for example, is to rewrite rules. So if the user has specified this rule, if child is true, age should be less than 18, rewrite this into not child or age less than 18. These are logical equivalent, but this statement can be evaluated in a data frame more easily than this one. So this can be done in parallel. So all columns are compared, and this one is just valid for one value of age and one value of child. So one of the things we do in validate, for example, package is to rewrite this. So let's have an example. I'm going to So one of the things we do in the validate is, for example, that you can specify a rule set. For example, age should be positive, should be a child. If it's a child, it should be less than 18. These rules can be plotted, and you can see then when we print the rules that we have rewritten this rule into age is bigger than 18. Or child is true. So we have done something more advanced. We negated this one. It's less than 18 and we changed it to bigger or equal 18, but we basically do some expression manipulation within validate. You can confront these rules and you can see the same thing when we confront the data. So age 20, child is true, age is -8, child is true, that we get. We do a confrontation and we do a summary, and we get for age positive 1 fail, so the second record is failing, and first rule of the second rule is 2 times failing on both records. You can see again that we did some rewriting, so we rewrote this one and we also rewrote this one. So because this is a strict, we allow some rounding errors. So correct for rounding errors in the evaluation of the rules. So how does this rewriting work? But we use quote. We can see what the expression is and turn it into a list or print a list. And this we can rewrite this expression into this rule. And this is just base R. You can use this script to rewrite and change the expressions. So we use this feature quite a lot. So in validate and validate DB to support SQL generation. So validate DB works on the database. Calibration translate it to a mixed integer program. This is modified to create modification statements. So R is quite powerful and using expressions. Another thing where I entered was with R was in statistical disclosure. So one idea we had is, could we create a detailed density map without disclosing details of an individual? And we created a package for that, SDC Spatial. So it works upon locations, so for example addresses, and we aggregate these into a rectangular grid, allow it to, and we visually assess the risk for disclosure. There's also a numerical. There's a numerical risk function which you can adjust, and it contains protection methods to protect the map. So, for example, if you look at dwellings, there is an example package dwellings within the package SDC Spatial. You can see that dwellings have coordinates in local coordinate system. We have a consumption and we have unemployed, true or false, and these are simulated, by the way. The patients are realistic, but the variables are simulated. So we can create a raster with that. Use the C raster, create dwellings, use the simulating data, and supply a solution of the raster, and supply lower threshold for what the minimum support should be for it to be valid or safe or not. So if you plot this, you can see that many points in the map are, so this is the map created. You can see that many points are unsafe, so red is unsafe, sensitive. We can apply a protection, a smoothing method, which smooths the values and creates a more smoothed version, and you can see that it also solves most of the unsafe points. And we can remove this unsafe point to make the map valid or to make it privacy protected. We applied also this method to a real case, so plotting education disadvantages. So it's used in a Shiny dashboard. Show you what it looks like. It's in Dutch, sorry about that. This is Amsterdam. Lots of neighborhoods, and what you can see is that it shows a very detailed map of where the educational disadvantaged children are within Amsterdam. It's detailed, but it's still privacy protected. So these locations there are living many children. Take care of that. There's a very low risk of disclosure. So that's one way of statistics. We use Shiny dashboards quite a lot. It's a popular product for government departments. Currently, we serve many dashboards for external use, so over 50. So, website for it. It's called dashboards.cbs. I created this with most work was done by a colleague of mine, but we created the infrastructure together. And one of them, which is completely in the same style as the CBS website. And these are all Shiny dashboards hosted on Zurich. And this is a very popular product for many government departments. So there are government departments that want a specific analysis of our data. Often they want to have it in the form of a Shiny dashboard. So that's a good thing. Another example where I was working with a Shiny dashboard is this one. It's a research project on the Dutch population, so the daytime population, so the number of people being present at a certain place in the Netherlands. This was based on mobile phone data, so how many phones were available at a certain location. You could see if there was an under or over presentation in each municipality. So you can see, for example, at this time, at Friday, 3 o'clock, June 1, you see that Amsterdam was very crowded at 3 o'clock, which is not that strange, of course. You can see that the big cities in the Netherlands were very crowded, or had more people than you would expect by people living in it. And you can use this dashboard to see how this changes overnight. Well, this. Put the link to the dashboard. This link. So what you can do, you can play this data set and it will change and show how the daytime population is going to sleep, goes to work, goes to the cities or the workplaces, and so this is all data. This is an old data set, so I think it would be quite different nowadays with COVID. Still, then then the working pattern was that. What we saw in the awesome list is that many statistical offices or many packages are available for publishing data, and that's a good thing. So most of the statistical agencies have an ICO database with an open data API. So, for example, Eurostat is a good one. Eurostat containing all kinds of data. The Census Bureau has one. By the Census, I don't think it's by the Census Bureau itself, but I'm not sure about it. World Bank has two, so VDStats and WDI. Because we have one statistical and CSM data are. So I want to show you some couple of examples. So this is just a Eurostat example. So if you use the Eurostat example, tidy words to make a selection, you can data set, so tips BP10 is the account balance for 3-year average of 2020. Just published, I think, last week. So we filter it on this period, 2020, 1-1. Can make a ggplot. So actually you can use this code to produce this graph, which is quite neat. So you can use data from an office just in your R script. That's not only useful for us, we have a couple of departments within our own office using Eurostat package to retrieve data from Eurostat to compare it or to use as auxiliary information within their own processes, which is very useful. So creating an R package for your data is really a good idea. Because it helps your mission of the institute, make it available. And it unlocks your data and removes barriers, and it really increases use of official statistics. So I know by example that, for example, our CDSO data package allows for retrieving data from the Open Data API. So it has a couple of functions similar to the Eurostat package: table of contents, search the metadata, but of course get the data. And it's used by lots of agencies. I've got to mention that it's also used internally. So we have at least 10 using statistical partners within our own office that use it to confront our own data with the data we published, or to retrieve data that was published by a different department. But it's also used by other government agencies. So the Court of Audit is using this, and on Twitter they named this package of the month because it was so useful for them to retrieve all kinds of data from Statistics Netherlands. We have a Netherlands Bureau for Economic Policy Analyses. We have also an environmental assessment agency. We have a public health department, and they all use this package to retrieve data. So giving external users the ability to select and retrieve data from your office is really helping your mission as an official statistics office. And also journalists. So we had an open data meeting last year, and for CBS Open Data, and there was a presentation of a journalist, and he showed some very nice graphics. And most of them were made with R, and he used this Open Data API R package, our CBS Open Data R package, to retrieve data from our database. He was very enthusiastic about it because he could produce graphics using R, and these were reproducible. So, current state as we see it right now is that R is flourishing in statistical offices. It's also a main language for data scientists. Of course, other languages like Python and Julia is a bit upcoming, but it's a main language. And what we also see is that there are many users of R that can or support the statistical process of statistical offices. So when you look at the awesome list, you can see that there are many packages within R. So most packages are R packages. So directions that I would like to give you is to go and explore and use R to improve your own statistical process. So use R to explore data patterns, outliers, do some visual analyses. Explore new statistical methods. For example, there's a connection with STAN. STAN is a Bayesian Carnot network, which is some very advanced statistical analyses and modeling and simulation. R has some very, very good packages supporting these R-STAN packages, also analyzing the results of these packages, which are really, really good. Well, also try to explore some new process methods. For example, there are a couple of new packages, for example, DuckDB or FST, to help in analyzing really big data sets in R sets. So, which are too big for memory, but can help in loading your data or analyzing data which is normally too big for your computer. Also, go and explore and look into new visualization methods. So one of them is GGDist, which is focused on printing or plotting distributions of statistical distributions, which is really a good thing. We should do more plotting uncertainty margins and distributions. Use R to communicate and report and popularize statistics from our offices. And for example, ggplot is used by the BBC. There's a package for that. bbplot, Financial Times, New York Times. So there are really some big publication offices that use R to produce graphics. And Shiny dashboards are also used in many places. For example, there's a ClusterBuster Shiny app this is from the RStudio website, to help hundreds of epidemiologists to battle COVID-19 in the Netherlands. So they use a Shiny app to monitor the COVID in the Netherlands. The other direction is production systems. So many production systems in our office are built with R, and I guess it's also the case in other countries. One thing we should do, I think, is to improve their robustness. So, because we're making R scripts for production, we should monitor package dependencies. So packages change, R changes. So one way to deal with this is using the package rm, which locks all your package dependencies and monitors them. The other thing is building process can also create a hierarchical dependency graph of your data. So typically the production process contains all kinds of data steps, data which depend on each other, and there are a couple of packages useful for that. One of them is, for example, targets. You define your own dependency graph of data and helps in creating these statistics. And the other one is, of course, for the long-term R version dependencies. So some processes you would like don't want to update too much, you can use either RM for rem or Docker for this. Whole language. So R's position is good because R is powerful. Remember, you can use it as a domain-specific language for all kinds of stuff, and it's used as a domain-specific language. It's the most official statistics-specific packages. You remember the awesome list, so it's over 70% is in R. But we can also embrace and learn from other languages. For example, Python, Julia, SQL, and use R tools to connect with them or learn. I don't think it's wise to start a language war or just learn from each other. So that was my overall presentations. I'm happy to take your questions if there are any.
Thank you very much, Edwin. Great presentation, a very good overview of what is possible with R and what is already done with R in your office, and I hope in many other offices as well. We have a couple of questions already. I might start just with the first one. The table plot visualization you've shown right at the beginning, it's great and quite generic. Do you happen to know other statistical domains where it is already applied? Or if not, can you think of any where it's valuable?
Well, I know it's not my domain, but it was used quite a lot by geneticists, so people working with gene statistics, because they like to compare all kinds of gene and sequences. So that's a very different domain, but I'm not aware of other applications of it. No.
Okay. I just read a small remark by Olaf Den Bosch before I ask the next question. So the remark is about the awesome list. So to all uRos participants who think the R package should be on the list, they can contribute and just send a pull request to the awesome list to input their package on the list. So coming to the next question, do you have ideas what the statistical community can do to get even more out of R? So in terms of standardization, user groups, finance projects, and possibly what the finance projects should have as topics and subjects?
Yeah, I think that R in the official statistics has is currently momentum, so I think it should. Yeah, I think we can profit from adding more momentum to it. So I think using R is a really great thing to do of improvement for creating official statistics. So yes, I do think sort of extra money helps, and also focus groups helps in learning from each other. But that's also the thing with my experience in using the packages I've written. When somebody starts using it, it always leads to improvements of the package itself, and improvements in our own process too.
Okay, the next question, I hope I hear a loud yes to it. Does it make sense, according to you, Edwin, to push for the use of R as opposite to proprietary tools, and for the release of open source code, for example, by introducing a provision in a future version of the European Statistics Code of Practice for it?
Oh, that's a good one. Well, I'm not in a position to make that call or to make that decision, but I'm a proponent of that. Yeah, I think that everything should be open. Yeah, I think working for the public means also publish our own scripts. Yeah. As long as it doesn't compromise the privacy of our citizens and enterprises, of course. So if there is source code that contains specific details on individuals, that's not a thing, of course, but as long as it's not doing that, I think we should be open. I'm not hearing you anymore, Alex.
Sorry, I should unmute that. It's 10 o'clock, but a very last question with maybe a short answer by you. What do you think is better, handle dependencies using RENV or avoiding volatile dependencies at all?
Well, that's a trick question. I think you should minimize your dependencies. That's a good practice to do. Yeah, but sometimes it saves your time to use a dependency. Yeah, but it's a really difficult question to answer in just 1 minute. Yeah,
that's true. Yeah. Thank you very much again for your great presentation and for replying to all the questions. With that, I will hand back over to Anna, who is also chairing the next session on sampling and estimation.
Hello again, everybody. Welcome. I'm going to introduce now the session dedicated to sampling and estimation. We will have here 4 presentations on regular mode and 1 lightning talk. For the first presentation, we have joint authorship by Austria and Switzerland. The presentation is entitled Synthetic Data with XGBoost and Advanced Calibration. And I'm going to invite Mr. Johannes GUSSENBAUER from Statistics Austria to present us. Johannes, you have the floor. Thank you.
Thank you very much. I'll share my slides. So, good morning, everybody. My name is Johannes GUSSENBAUER. I'm from Statistics Austria, and I'm going to present some work that myself, Matthias, TEMPL, Siro, FRITZMANN, and Alexander KOWARIK did on generating synthetic data with xgboost and advanced calibrations. So to give a little overview of my talk, I will give you a quick intro on the R package that it's all about. So it's the R package Sympop that the 4 of us worked together on. So not really together, but Alexander KOWARIK and myself, we worked on improving a calibration part of the package, and Matthias, TEMPL, and Siro, FRITZMANN, they worked on improving the modeling aspects of this package. So we thought we had something going there and wanted to present this at this conference, basically. So let's dive right in. So what is the Sympop package all about? The title of my presentation said something about synthetic data, and this is basically what this is all about. The Sympop package is able to generate synthetic microdata. Specifically, we're talking about household data. So we want to have data where we have people who live in households in a region or in a country or whatever. So we want to have like really the household structure as well, and have household variables and person-specific variables and this kind of data sets. This is the point of this package, generating synthetic data for this. And for everybody who's not familiar with the synthetic data generation or why this is useful, usually you want to, or as a statistical institute, you might want to release as much data as you want, but you're always restricted by national data protection law or the GDPR, which are of course very useful and very needed. But nevertheless, the scientific community or the public could really benefit from having good microdata, which is not highly censored, and generating synthetic data could be one way to limit this burden on having access to good quality microdata. So what the synthetic data should, of course, do is not reveal sensitive information and have, like, I say here, preserve the correlation structure, have a quasi-identical distribution. So basically you want to have synthetic data which mimics the real data very well, but you also want to don't duplicate your data. So you want to not be able to single out individuals and so forth. And what you can expect synthetic data to be used for is, for one thing, prototype development. So you can have, like, basically your synthetic data out as a statistical institute and have people do the modeling on it. And when they're done doing the modeling on it, they can say, well, can we maybe run our models in your office and you give us back our results on the real data? Because it's not that you're giving away the real data, it is a synthetic data set. So you, the models might not be the correct ones, but still the public or the scientific sector can really do some good analysis beforehand. Or you could also do it for microsimulation, have the synthetic data as plugin for a good microsimulation, basically. So the Sympop workflow is you start from a sample or and have census tables. You could also start from the population itself if you happen to have this. If you start from a sample, then you want to calibrate your survey. You don't need to calibrate it if it's already is calibrated. And then you start basically your generation steps, which is defining some household structures. This is how we call it in this package. So you have these basic household variables and you have a household structure defined where you say, okay, some variables I want to draw from my sample basically and do not want to simulate them because it gets too difficult. And then you start modeling variable by variable. So basically you start modeling something like education, then you start modeling income, and then you start modeling work status or something like this. So then you start modeling and modeling and modeling. And then you do this geographic allocation, which is basically the calibration step, which I will talk about. And after this, you will have your synthetic population, where only a small part of it is basically drawn from the sample that you have in some kind of way. There are different strategies to draw from it, but everything else is simulated. And then you do this allocation as well. So you should get quite a good synthetic population data out of it. And yes, we've already used this in some work as well. So for the modeling, this now is the improvement parts. For the modeling, you had some options how to model variables. You had linear regression, you had regression trees, etc. But what Matthias, TEMPL, and Siro FRITZMANN did, they included the xgboost package to Sympop, which is a great contribution basically, and it's the xgboost package. I'm not sure if we're familiar with, but it has really good properties. It's very good out of the box method basically, and it's very well implemented. So the R package for the xgboost is very well implemented, also performance wise. So this is really a really good contribution to it. So now you can, during the Sympop data synthesis, use this xgboost packages for simulating your variables. And basically this is what this looks like. So if you want to simulate a categorical variable, you can have your Sympop object here and say now method xgboost. Now you will be able to use the xgboost package behind the scenes. And you could also, using this extra parameter model params, overload the default values of the method. So there's lots of tuning for this xgboost you can do. You can also use your own objective function if you really know what you're doing. So you can overload all the variables using this model parameter and use the xgboost when simulating categoricals, but also continuous variables. So they basically widen the scope of the model possibilities. Now here's just a quick example on what the benefits is. They Matthias TEMPL and Siro FRITZMANN did a lot of different simulations on this. And here's just one comparison simulating a categorical variable from the EUCIRC data set. So I think one of those is like some health variable and the other one is marital status or something. But the point is basically using the multinomial approach, which was already implemented. We get basically higher divergence. This is basically the scale says how much do I diverge from the target where I started from. So I get higher divergence from the actual target population where I want to go when using the multinomial model naively, but using the XGBoost, which has a stronger out-of-the-box like performance basically. These colors are more transparent and basically means I'm getting closer and closer to the true or to the target population that I want to model basically. So with the XGBoost, we just included a good out-of-the-box method, which lets me have good simulations for my synthetic population. With the continuous variables, they also did some tests, but they weren't as successful. So you need to tune the XGBoost more in this case to get better performance. I'm just looking at the time a little bit. Okay. So now for the calibration. So what you want to do with the calibration, if you have your synthetic population. So if you've done modeling everything, then what you want to do is probably fit your population to a target distribution. Basically, you want to say, now I have all my individuals simulated, and now I want to have my age structure according to the census. Or when I want the share of male and female according to the last census or to the last published tables from the Statistical Institute. And this is basically what you want to do with your synthetic population. So I have here like my population, which has way more than these couple of individuals in there. And all of these circles, they say, okay, this is a household basically, and those are single households. And I want to have like this kind of target population here, and I want to have this aggregated from those. And if I do not have a household structure, then it would be very easy. I could just say, okay, I want 120 of the green ones and 80 of the gray ones, and so on and so forth. But since people are living in households, this is a bit more of a difficult question, because you cannot break apart the households. So the question with this calibration is, okay, how can I select these households that I can fit any target distribution that I want? And this is a combinatorial problem, which is not easy to solve. We use a heuristic for this. So we use a simulated annealing, which is included in this package to solve this. So you start from your synthetic population and say, okay, I want to really fit now my synthetic population to have a good age structure, which is really fits the age structure of the statistical office, basically. And this is where we did some improvements on it. So now, because we did some projects there and we had to use multiple different distributions, because you don't have like the combined distribution on age, gender, working status, but you maybe have one distribution on age and one on working status and one on gender. So you have now the possibility to include multiple distributions into this calibration step. So the whole simulated annealing takes care of trying to fit multiple different distributions which are not connected to each other. And that meant that we had to rewrite lots of code, and also had to adjust the objective and the sampling probability of the simulated annealing procedure. So now our objective for, if we have P different tables, our objective looks now like this. So it's basically just squaring some of these arrows. These are the arrows basically, which I want to have my estimates and my target. So this is basically a simple extension of having just one target table, basically, on one target distribution, and also for the sampling probability, how you draw and how you select basically these different individuals. We also had some extensions here where it's now possible to include multiple tables, and this still terminates, so this still works quite well. the whole procedure. So we're still going to at least a local optima here. And also here just a quick, also something that we improved it here, just a quick picture on giving an idea on what we did with improving in terms of speed and memory. So this is really using the example data from the Sympop package and generating populations from 100,000 to almost 5 million people. And the calibration now takes here a bit more over 2 minutes. This has, we have to say here that using the example data there's always the example data is chosen that it's not difficult to calibrate it. So you have, maybe if you want to simulate or synthesize the population of a whole country, this will not take just 2 minutes, but maybe a couple of hours. But the point is that it does terminate quite quickly. So you will get a good result basically, and you can deal with it with not that much memory. So you should expect to run this on a not supercomputer style, but on an average laptop or something. You should be able to run a population with a couple million individuals. That should definitely be possible now. So yeah, these are the improvements that we did for the Sympop package. Now you can, we also tested this and we were quite successful with deploying this. So it's definitely feasible for Austria, which has like 9 million people in a population, but we also tested it for other populations where we go over 100 million people, and it's still feasible and doable. So it's a good contributions basically. So yes, there are some references, and I'm happy to answer any questions if there are any.
Thank you very much, Johannes. We have one question, yes, from Adrian Dusha. Is the simulated data multivariate similar to the source data?
It's conditional. If I understand it correctly, so we're not synthesizing the whole multivariate distribution of the original data, but it's only conditional to what you put into the model basically for predicting your next variable. So the distribution is similar, conditional to always the model specification. So the model all the variables which you use for your modeling. So it's not that you synthesize the whole multivariate distribution. I hope this answers the question more or less.
Thank you, and congratulations for your work in improving the calibration, which is a very important topic for estimation and sampling. Okay, we'll move on now, thank you again, to the next presenter from Statistics Poland, Mr. Sebastian WÓJCIK, which will talk about measuring inequality in sampling surveys. Sebastian?
Hello, everyone. Can you hear me?
Yes.
Okay, I will share my screen now.
Okay.
Is it visible in full screen, my presentation?
Yes.
Okay. Good morning, everyone. Sebastian WÓJCIK from Statistics Poland. I wish to say a few words about our in-house work in preparing inequality measures for sampling surveys. A short introduction to the problem. Our core activities is to conduct the sample surveys, and a crucial part of sample surveys is the sampling error. It has a strong impact on reliability of provided estimates, especially in terms of precision. Information about estimate totals, means, and so on, all the statistics, must be completed with precision or confidence interval to make our information complete and to show degree of reliability of a given figures, numbers we provide. And sampling error is strictly connected with sampling design, inclusion probabilities, and sampling weights. And methods that are used for sampling servers must take into account data weighting, and data weighting weights itself play important role in calculating the precision of estimates we provide. There's a domain of inequality which is of interest of many scientists, including economists, sociologists, and statisticians. For example, there are several or even plenty of notions of inequality in economics. For instance, income inequality, lifetime inequality, inequality of health, and so on. So you see, it's domain richly researched by scientists. Scientists developed inequality measures starting from variables on ratio scale. For instance, all of income inequality measures of income inequality are suitable for ratio scales, but also other measures were developed, for instance, for ordinal scale, which is also of interest. About R, we should notice that R package should be implemented with methods suitable for weighted data if we want to process sample survey data to make it unbiased. In the case of inequality analysis, when I check CRAN packages, there's lack of packages that offer a wide variety of inequality measures, as well suitable for data weighting and provide precision of given equality measures. Since it's a sample survey, we don't give estimates with full reliability. It also we should include precision of estimates, for instance, inequality measures. So it led us to idea to create a package that covers wide spectrum of inequality measures, including weighting, by using or extending available packages like Inec or sampling, and adding new content. After our package is tested and enhanced, it will be available on GitHub account of Statistics Poland. Okay, so simple introduction to inequality measures. In INEC package, there are some measures already available: Atkinson coefficient, Gini, Cohn, Ricci, Schutz, tail, entropy, and coefficient of variation. We added new Hoover index, Jenkins index, Cowan/Sherry index, Palmer ratio, 20-20 ratio, Letty index, and Allison and Foster index. Few words about them. Jenkins index and Cowan and Sherry index are indices based on generalized Lorentz curve. Palmer ratio and 22 ratio are ratios of deciles. Palmer ratio is ratio of last decile to the fourth decile. 20-20 ratio is a ratio of 8th decile to the second decile. Letty index and Allison and Foster index are developed for ordinal scale data. And we took all these measures and implemented in R with the possibility to weight the data. Some notions showing how formulas of inequality measures changes in the case of changing unweighted to weighted data. So for instance, we have Gini coefficient or Hoover index. So in general, we replaced n number of objects with sum of weights. And each case we sum up data, we need to multiply by weights. So further, we have classical tail index, Atkinson coefficient, and I will introduce Leti index and Allison-Foster index, which are developed for ordinal scale. So let C be an ordinal scale. C1 is the lowest item. M is the highest item value of that scale. The special case of ordinal scale is, for instance, Likert scale, 1, 2, 3, 4, 5, for instance. And I is frequency of CI, and F, capital F, is a cumulative distribution of cumulative frequency. So notice that Leti index is just based on cumulative frequency. We don't incorporate ordinal scale values into that measure. In the case of Allison-Foster index, we calculate mean value below median, mean value above median, and we subtract mean value above median from mean value below median to obtain Allison-Foster index. Notice in that case, cumulative frequency is used, as well values, particular values of the scale. Okay, let's go to the R package. What we have done. First, we did that simple exercise to derive inequality measures formulas for weighted data, as I showed you previously. Next, we coded for new formulas. In the case of inequality package, we took this measure already available and extended to possibility to weight the data. The intermediate results are obtained by Inequated Function that delivers all inequality measures for a given data set. And the final function is Inequated boot that extends the output of the previous function by the results of bootstrap. Okay, so in particular, we have 15 inequality measures defined in the following way. In each case, weights have a default value, all weights equal to 1. In the case of particular measures like Atkinson, Colm, entropy, and Jenkins, additional parameter is required already with default value. Also, in the case of Jenkins function, since 2 indices are based on generalized Lorentz curve, we produce both within one function Jenkins, since when generalized Lorentz curve is obtained, then it's easy to get Jenkins index as well Cowell and Flesher index. Next, we have Inequated Function. So we take all parameters of particular functions like Atkinson, Jenkins, entropy, and Colm with default parameters. Also X the data and W weights, and the function generates weighted mean of X, weighted sum of X, and all inequality measures, of course, after including data weighting. And that functions is used, it can be used for intermediate, for the results, or intermediate function for the final one, which is Inequated boot. So you notice that all parameters from the previous one are already put into that function, but we have many new parameters connected with bootstrap method and with calibration. So we have B number of bootstrap samples, parameter keep samples, which is, if it's true, then returns bootstrap samples of data and weights if needed. The second one, keep measures. If true, it returns values of all inequality measures for each bootstrap samples, and it might be further processed for other purposes like statistical test, which will be showed in an example. By default, we perform naive bootstrap. It means weights are not calibrated. Elsewhere, if that parameter is set to true, then calibrated bootstrap is performed. By default, we calibrate just to the initial sum of weights, but with the function calib from the package sampling, we can perform calibration for several x's, additional variables, several totals, and with 1 out of 3 or 4 methods of calibration available in that package. What is the output? As previously, we provide weighted mean and weighted total of x and all inequality measures. And for all of these statistics, we provide expected value, bias, standard deviation, coefficient of variation, lower and upper bound of confidence interval produced by parameter confidence alpha, which is by default set to 0.05. As an example, in the package INEC, there's a data course is income metadata from surveys conducted by Philippines National Statistics Office, and it covers data of income of the household, who is the head of a household, man or woman, number of persons, size of household, as well weight of given household. So it's a good example to use our inequality measures in such a version. So we shall compare income inequality among men and women heading a household. To this end, we produce 2 samples, bootstrap samples for female head of household and male head of household, 1,000 bootstrap samples. First, we wish to visualize Gini coefficient distribution with ggplot2 package. So we produce a relevant data frame, and with geom density, we produce density plot. So we may notice that distribution of Gini coefficient for females is flatter than for males. Also, we may notice that expected value for males should be higher than for females. So we want to check if the difference between inequality Gini coefficient for female and male is statistically significant, that difference. So the first step, we use norm test package and the function JB norm test to check if these data are normally distributed. So we see that p-value is greater than 0.05 in both cases. So we can use these methods that are based on underlying normal distribution of variables. So we use t-test of mean difference. We notice that p-value is lower than 0.05. That means that mean value of Gini coefficient for a woman heading a household amounting to 0.4129, and it is significantly lower than for men heading a household, and that mean Gini coefficient amounted to 0.42678. So even that Gini coefficient in general will be produced and we see the difference, the test and the relevant parameter KEEP measures allowed us to check if the difference is significantly lower or not in such a case. Okay, thank you for your attention. I'll be happy to hear your feedback in a case what should we add to our package, and share your ideas or comments or remarks, what should be included to make it more complete. Once again, thank you for your attention.
Thank you, Sebastian. We have one question from our colleague, Marian Necula. Do you plan to provide also confidence intervals for the inequality indices as direct auxiliary output rather than indirect from the calibration output?
I don't know if it's possible just directly for those measures, since in many cases I can provide confidence intervals, since I know that there's a kind of distribution underlying that measure. Without distribution, I cannot provide confidence interval if I understood it correctly. So I derive it based on Bootstrap at this moment.
Okay, thank you very much for the answer. Congratulations for the work and good luck. Thank you, Sebastian.
Thank you. Thank you.
Now it's time to move on to the next presentation, which is Adrian from Romania, who will talk about missing values treatment in R. Adrian, you have the floor. Thank you.
Thank you. Thank you very much, Anna. And good morning to our European viewers and wherever the others are in the world. My talk relates to missing values. Well, in fact, it relates to survey research. And within survey research, it inevitably relates to the question of missing values. I'm not sure, did I just shared my entire screen instead of well, I think it's looking. Okay, so the typical missing values in R is just an NA or an NAN to signal operation that results in not a number. But typically, the NA is the only symbol in R that specifies missing value. And there is absolutely no information why this value is missing. It's just missing. To make a parallel with an Excel sheet, it's just an empty cell. You don't have any information about that cell. Now, in survey research, empty cells are, of course, possible, but usually values are missing with a reason, and those reasons are recorded because the respondent might refuse to respond, because the respondent doesn't know, because it's not applicable, or because a certain situation might not apply. Some questions, for instance, being only specific to a certain category of users and not another. And then there is a reason why that particular cell is empty in the data sheet. Now, there are important reasons to know why certain values are missing, right? Because respondents who do not know what to respond are qualitatively different from those respondents who do not want to respond. So they are part of different populations or different subpopulations. And that is important because knowing which subpopulation a certain respondent belongs help imputing the missing values. For instance, that's one application of knowing the reason why missing values are up there. And then, of course, related to the concept of missing values are categorical variables, which traditionally in R, they are factors, and they are considered the main method to represent such categorical data. They are flexible, easy to use, but the underlying values representing each category are lost. So if, in fact, my questionnaire denotes 1 and 2 for, let's say, yes and no, and 97 for not applicable and 99 for don't know, when I represent that with a factor, the underlying values are lost and they become 1, 2, 3, 4 by default. And it's not possible to specify that some of the values should be considered missing, so 97, 99 should not be considered there. And that's a simple example, but it might be age, it might be whatever. these values could be different. And then how do other statistical packages deal with that? SPSS has one of the most flexible ways, either declare missing value, either this discrete, why 3? Because they are bounded by their graphical user interface, right? And but they solve that by allowing a range of missing values between a minimum and a maximum. And then Stata and SAS allow for any number of discrete missing values, but they store it not as a number, but actually as a symbol like .A, .B in both Stata and SAS, using different memory representations, either very, very high, close to the very limit of the memory representation in of numbers, or very high or very low. I'm not sure which is which, but this is how they represent it. And a single dot represents the completely missing information, that empty cell I was talking about. Now, how do we do that in our most recently Package Haven does that and proposed a solution. And they use the ReadStat library implemented by Miller to import and export between various statistical software. And they implement these two new special types of object called labeled and labeled SPSS to represent categorical variables. And how is that working? This is the command to construct the labeled SPSS object, where we have values from 1 and 7, where 1 is bad, and suppose this is a response scale from 1 to 7. And then they do print the actual values there, where 1 represents bad and 7 good. So they actually print the categories for each of the numbers there. And they also can specify missing values along with the command with the argument NA values there. So if we add a number 99 and we specify that is missing, it is recognized as a missing value, number 99, and it's also represented as a category refusal. Notice, however, this is printed as a number, not as a missing value, despite this number being recognized as a missing value. So this is identified as missing, the last value 99 we just added, and I can index that and I can see it's number 99, but it is still part of the base calculations. For instance, if I took the mean of that object, it would give me a mean of 15, whereas the response scale is from 1 and 7. So the number 99 should not be part of the calculation. That is, of course, correctable. Everything is possible in R. So Package Haven does not allow to ignore that value in the calculation. It's not possible to ignore it, but we must manually remove it. Like, for instance, there is the related package label there, and then we have to use this function to actually transform all the user-defined missing to actual missing in R, and then take them in using the NA remove argument of the mean, and then we will get exactly what we are looking for. But this, to my eyes, this is ugly. And that was the reason why I started, and this was actually the prelude to what I am actually going to talk today about the declared way, which is actually a special package that is published now on CRAN. It's called declared. Now, package declared, because I like Haven, but I didn't like that particular part of treating the missing values. And package declared follows a very similar approach with a very similar syntax. But there is a fundamental difference between Haven and declared. Well, Haven stores existing values like the 99 value we just saw, and interprets that existing value as missing, while package declared stores NA values and interprets them as existing. So in a shell, we attribute different meanings to the same NA underlying NA value. So what I am actually storing is a pure NA value, but I attribute different meanings, and I do that by storing some information in the attributes of the variable. And the syntax, as you can see, is very similar. Instead of labeled SPSS, I just use declare. I see exactly the same input vector, exactly the same labels, and exactly the same argument, and this is 99. Only this time, this value 99, as you can see, is not just a number, it's identified as a missing value, a missing number. The rest of the printed object looks exactly the same. The exception is the declared missing values are identified, this time identified as missing. Now, these are printed as regular NAs, and do note the difference, for instance, between the two ways of calculating the mean. In package declare, once I declare the value to be missing, it's automatic to create a different representation of the data. I like based on, and I like it. And those values are automatically identified as missing. It plays natively with the NA omit and NA remove. That's natural because they are actually represented as missing, pure missing values in R. And as a bonus is recognized by most functions. So if any statistical procedure, for instance, really wants a factor as an input, then the function toFactor from package label is recognized, and the declared object is the same with the function toCharacter. And towards the end of my presentation, this package is already incorporated into other metadata specific R packages. For instance, DDI with R. DDI comes from the Data Documentation Initiatives, which helps converting data, including the missing values, between various statistical software. For instance, a hypothetical SPSS data set called test_sub, and I just use this function convert, and it will create a similar file data.dta in the same directory where that file is present. And what it's doing to convert the missing values, it aggressively searches in all variables for similar missing codes and consistently using the same letter everywhere. So if 99 is the reason for a typical non-response, then the same letter is used in all variables using the number 99 as a missing value. And this is something no other conversion package does, conversion software, including the commercial ones. So thank you very much for your attention. I'm going to stop sharing my screen. I hope I did not take it over.
Yes, it is off your screen.
Yeah.
Thank you for this work and for sharing with us your contribution in the R community. Good luck. I see there are no questions in the chat.
Can I ask one short question?
Okay, please.
How would you handle the problem that when you use these kind of methods to store the missing values, that it's really hard to apply just a standard set of functions to the data you have in this format? How would you deal with that?
Yeah, it's easy. You just use the double equal. And it's automatically searched for double equal 99, and it will automatically find all of those missing values with a specific code. Or you can use greater than equal. So it plays nicely with all the base functions that you would normally use an indexation for. So you can actually search for particular missing values in your data and sub-select for those values. No problem at all.
Okay.
It's already embedded in the package.
Okay, thank you. And we have one question from Mark. Congratulating, very nice package, Adrian. I really like the interface. Is it possible to select different missing values?
I think it's the same question.
The data according to missing Right.
Yeah,
Yeah.
it's the same
Yeah.
kind of question. Yes, it's possible to filter. It's possible to index based on equality, non-equality, greater than, lower than, whatever things people usually do in Bayes are. It's already embedded in the leaflet package.
Very good work and complex. Good luck and thank you for the presentation.
Thank you.
Okay, we'll continue now the session with the last regular presentation from Spain, minimizing mean squared error in the rolling windows implementation. And I think the speaker will be Mr. Virgilio Perez. Am I right?
Yes, thank you. Good morning, Ana Maria. Well, I share my screen. One moment, please. Second screen. Okay. Well, dear speakers and colleagues gathered at this event, good morning. I am Virgilio Perez from the University of Valencia. And firstly, I would like to thank the opportunity to communicate the progress of our research at this event. Well, with your permission, I begin with the exposition of our work entitled Minimizing Mean Squared Error in the Rolling Windows Implementation. When conducting research, it's often impossible or too expensive to collect data from all the people or items we are interested in. Instead, we take a sample of the population of interest and predict how the population behaves from that sample. There are a lot of aspects that influence how much a sample resembles the population and thus the validity and reliability of our conclusions. One of the key concepts to consider when conducting research is sample size. It is well known that as more and more information becomes available, the uncertainty reduces. For that reason, in this study, we have focused on how to extend the sample size without the need to obtain new data and without barely increase the associated error levels. As we say, sometimes we cannot validate our research because we have little data, a circumstance that causes a lot of volatility. To solve this problem, we propose to use adjacent information, that is, to admit that close subjects behave similar. To verify this assumption, we used a large database with more than 1 million than 150 variables and more than 1 million observations over 30 years. We have prepared this large database from the data offered by the Sociological Research Center, a Spanish public institution with a long story in public opinion studies. We have found that there are indeed certain time variables that evolve very smoothly, such as political ideology, among others. So it is reasonable to establish data clusters. The proposed method describes the use of the rolling windows, achieving the described objective of increasing the sample size without barely increase the estimation error. In descriptive statistics, we use measures of position to summarize all available information in a single value. It is well known that any measure of position must be accompanied by a measure of dispersion, which confirms or not whether the statistic used is doing its job correctly. We also know that as the sample size increases, our predictions will become more reliable. Unfortunately, it's not always possible to have the desired volume of data, either because of the high cost of obtaining them or because they are unavailable. This study presents a methodology that allows us to increase the sample size with little compromise on data quality, thus allowing us to obtain more reliable estimates. Well, as we know, the sample mean is an unbiased estimator of the population mean. This action will serve as a reference in this study, in which the calculations are based on this estimator, the sample mean. As we say, increasing the sample size reduces the estimation error, in our case, the standard error of the mean, obtained as the quotient between the standard deviation and the square root of the sample size. We assume statistical independence between the sample values. But how do we increase the sample size? Our hypothesis is that the value taken by a variable v observed on a subject S1 does not differ significantly from the value taken by the same variable v observed on another subject S2, provided that the rest of the characteristics of S1 and S2 are similar. The aim is to show that the cost of taking these close values is lower than the benefit obtained, a circumstance that allows for improved predictions. To carry out this research, we have used a database with almost 1 million observations, in which 3 discrete variables are distinguished. Age, which takes values between 18 and 99, the time variable, which takes values between 1990 and 2021, and the observed variable, which takes values between 1 and 10. We therefore have a sample size for each age-year combination, thus to improve the estimation of the ideology of persons with a given age I at different points in time t, taking into account only the data corresponding to the vector I t. The proposed methodology will improve the estimates obtained, since it considers not only the sample units contained in IT, but also those of its neighbors, increasing the sample size, but without increasing the variability. From the previously mentioned database, we have been prepared 4 tables: sample size, mean, variance, and standard error of the mean. By these tables, we can make a composition of place on the sample under study. The information contained in these 4 tables will allow comparisons to made with respect to the data generated and to verify whether the proposed methodology meets its objective. This slide provides the sample size table as an example. The types of windows used in this study were as follows. The 1/3 window means that the years before and after were considered to obtaining a sample size of approximately 3 times the initial one. The other 5 window types were used a similar way, obtaining a sample size 25 times larger than the initial one in the 5/5 window. As can be seen, the evolution of the average, taking age 20 as an example, is smoother as the sample size increases. However, the aim of the present study is not to increase the sample size, is to obtain a good estimator. We are therefore interested in keeping both the standard error of mean and the mean square error of the proposed estimator as small as possible. Therefore, we must minimize the variance of the estimator to this end, and although we assume that the variable and the analysis evolves smoothly over time, that is, the value at time t does not differ excessively from the value at time t more or less 1, we consider it appropriate to weight the different values differently. In this way, we will reduce the distortion caused by using values that do not correspond to the original sample. we have been carried out some calculations based on 5 scenes, establishing different weights. In E1, we have worked with equal weighted windows, that is, the proposed weights coincide with the ratio of the sample size of each subset to the total sample size. In E2, we have proposed a set of weights that satisfy 2 fundamental conditions. Subsets further away from the origin subset are assigned a lower weight, and symmetric subjects are assigned the same weight. The proposed weights for 1x3 and 3x3 windows are given here as an example. In E3, all weights are the same. In E4 and E5, we have been calculated the variance minimizing weights with one difference. In E5, the constraints applied to E2 have been added. To perform all these calculations, we have used the QuadProc method, quadratic programming or QP, of the ROI package, R optimization infrastructure, developed by Karl Hornig and other authors, implementing the appropriate restrictions in each of the scenarios described above. This slide provides the code used for 3x3 window. At the moment, we are developing an R package that facilitates the calculations for any window size, also allowing to implement the weighting that the user deems appropriate. As shown in this graph, increasing the sample size by using close values does not reduce the mean square error, at least not always. However, there are substantial differences between the different scents proposed. Only values between 2.5 and 5 are shown, as this range includes the mean square error of the initial sample. Therefore, values above this range are automatically discarded. In fact, as age increases, that is smaller sample size, more and more values are discarded. The following figure shows the rates of variation between the mean square errors obtained in the different scents and the mean square errors of the original sample for a 1x3 window. In this graph, the blanks show a 0 or positive rate of variation, that is, those I per T combinations for which the mean square error of the window does not decrease. As can be seen, E1 and E4 are the scents where a greater reduction in the mean square error is achieved, although not for all I per T combinations. In contrast, the weights proposed in E2 do not reduce the error. Notwithstanding the above, we also wanted to compare the average bias in each window and scent. The results obtained show that E2 is the scent in which, on average, the least bias is generated, except for the 5x5 window, with E5 being the scent in which the best bias is generated. It has been observed that, despite what might at first appear to be the case, the estimation error increases when the proposed weights are used. However, it is precisely with the weights set in this scent that a lower bias is obtained. We consider that this research allows further progress to be made in the search for the best estimations. Well, and that is all. Thank you very much for your attention.
Thank you, Virgilio, for your presentation and your work. I cannot see any questions in the chat. Then it's time to continue the session with the last presentation, which is a lightning talk from Azerbaijan, titled Using the R programming system in Sample Surveys. I think the speaker should be Mr. Mubaris Nuriev or Saleh Movlamov or Mrs.
Yes, I am here, but with us, we're
Welcome.
talking Mr. Saleh Mevlamov.
Please share your slides with us and good luck. Yeah, we cannot hear you, Mr. Saleh Movlamov. Please turn on your microphone.
Yes. Okay. Can you hear me?
Okay, we can hear you now. Yes.
Yes. First of all, I want to say thanks to organization committee, Statistical Institute, particular to Anna Maria, who invite you to conference. Then
Thank you, Mr. Saleh. And please just let me mention that you have 5 minutes for your presentation. Thank you.
Yes, 5 minutes. Abone açılmadı. Presentation. We are from Center of Scientific Research and Statistical Innovation, State Statistical Committee of Azerbaijan. Name our presentation using raw in sampling and estimated process. We here want to show you sampling process and estimated process. Allocated sample frame by region and urban area show in this code. Grouping and urban and rural area will show in this coding. Sampling process of region, urban and rural will show in this coding. Save as result show in next coding. Estimated in raw. Estimated process we use also average indicator. Average indicator. In order to calculate it, average indicator, we are using also standard program. Standard program was preparing mathematical rules, but all mathematical rules now based classical mathematical rules. I use here model code for preparing program. I do not use standard program because standard program have several errors. Here we using a number of household and population census data. Calculating average rules, calculation or average rule is not. I use also intelligent intelligent. If here we use if n1 more 0 and if 1 0 because this rule needs very good rules. Estimated variance for population. Estimated variance population calculated total variance of household consumption expenditure of region calculated for this rule. Here I want to show what rules, mathematical rules, use it. And in order to preparing our article, we use this reading. Thank you for attention.
Thank you also for sharing your work. Good luck in improving and in your research. And this is a very good, you make the first step in using R in your statistical office. Okay, so the session is closed. Thank you very much, all the presenters. Good luck in the work. And please enjoy the next session, which is dedicated to big data. And I'm inviting my colleague Alexander KOWARIK from Statistics Austria for the chair. Thank you.
Thank you, Anna. And we will start with the next session immediately. So the next session has 3 presentations on applications on R to big data. And of course, you all know that you can use R for the big data nowadays. There used to be a time when the first thing people mention when you say you use R that, yeah, but what about a big data set? Can you use it? That's obviously was back in a time when a computer had just like 1 gigabyte of memory, then it was hard to use. So without using any more time, I would ask, stop presenting, and I see Andrea already started his camera, so he will be the presenter for the first presentation, R for big data processing online job advertisements. Please go ahead and share screen.
Yeah, thank you, Alexander. Please let me share my screen. Okay. Okay. I hope it's no, not yet. Okay. Okay, you should be able to see my screen right now. Yeah.
You see the screen, but yeah, you see the presentation in presentation mode.
Yeah, okay, fine. Yeah, thank you very much for the opportunity to be presenting here at the uRos conference. It's the first time for me. I'm I have to say a beginner with R, but of course I've been collaborating in this project also with more experienced colleagues. So this is a joint work I'm presenting here, but Matthias Mesaros, Fernando Reis, and Gabriele Marconi, all from Eurostat, have collaborated to this work on using R to actually to process online job ads. So here the big data we are referring to, it's online job ads. I will so the outline of my presentation is I will first go through an introduction on online job ads, what we are talking about, which data source is this. Then the indicator, which is the objective of our project, and then a glimpse on the R code and the main challenges that we have faced. So without going into much detail, and then a little bit of results and future work. So it has to be quite short, but then I will redirect you for further information on other sources. So online job ads are actually advertisements published on the web, revealing an employer's interest in recruiting workers. So we usually refer them briefly as OGA, so because it's a very long name, but usually this OGA includes a lot of data on the characteristics on the job, so that can be extracted from the advertisements found online. So then you will have information on, for example, the occupation type, the location of the job. Then you will have some characteristics of the employer, like of the name of the employer or the economic activity, and also some requirements, for example, skills, education level, then maybe you have other information on salary and so on. So you will have a lot of information available usually. So it's clear that these data source has a huge potential for complementing official labor market statistics with more granular data and perhaps more timely even. So we have availability of online job ads at Eurostat thanks to a joint project and a cooperation and a formal agreement between the ESS and the European Center for the Development of Vocational Training, which is CEDEFOP, is an EU institution, it's an EU agency, and so then these online job ads are collected from the web via APIs or for some portals and scraping in other web pages. Then we have these OGAs are part of this big initiative that we have at Eurostat under the Trusted Smart Statistics umbrella. So statistics using new data sources, new non-traditional data sources and big data sources as well. And this is particularly part of the what we call Web Intelligence Hub. So a series of projects and use cases aimed at using data sources from the web. And this is one of actually the flagship project. So then OGAs for these on the Web Intelligence Hub are actually scraped or downloaded for 27 EU countries plus the UK. And then we have more than 100 million distinct online job ads collected for 316 distinct sources for 2019 and 2020, which is actually the period of our analysis for the study. This is an example of how the structure of online job ads would look like in a tabular format, stored in our Amazon Athena service. So you can see that you have, of course, a general ID. Then you have some dates regarding the extraction of the ads from the internet, and then you have all the information that you can find, actually scrape and recognize from the text of the ads and other information usually available. The main variables that we used for this study are the grab date, for example, which allows then us to frame the ads in a specific period of time. Then information regarding the location, so ID, city, province, and country. Language, information on the occupation type, the name of the company advertising the job, and information on the contract. So this would be then the structure of a typical online job ads on our data set. A little bit of background. So this is the work that we have done here. It's an extension of a case study proposed by the participants of the SNet Big Data 2 project, and especially work package B, who worked on actually the calculating this labor market concentration index using online job ads. So, and the first use case done within this SNet project presented the results for Germany, and it was based on a research paper from Azar et al., an American scientists, on the calculation of this concentration index in labor markets using burning glass data. What we have done here is we have adapted the code and extended it to cover all the 27 EU member states, but so the original work and proposal is coming from a joint endeavor of the ESS. Then to go to the actually the results, also not the results, but the objective of our study then is to calculate what is called labor market concentration, which is basically an indicator that could answer the question how much choice people have when looking for employment in a specific labor market. And a labor market in our study is defined by specific cell defined by 3 dimensions. So for a given occupation, so the occupation type, the region, which in our analysis it's the functional urban area. So we are concentrating on urban areas which then are better suited to capture an urban labor market, and time, which we use the quarterly dimensions in our study. So then, of course, labor market concentration means that a high level of concentrations means that there is a high competition between employers to secure the workforce, whereas in a low, sorry, it's exactly the other way around. So in a lower market concentration, there is a high competition between employers, whereas the labor market is highly concentrated. It means that the hiring opportunities are actually concentrated in the hands of few employers. This means less choice for workers, and eventually low bargaining power, and worse conditions and lower wages and salaries. This is expressed by the Herfindahl-Hirschman index, which is an index used for calculation of concentration in markets, usually for assessing the competitions after mergers and acquisitions. So it is a well-established indicator. It is based on the sum of the squares of the market shares of each company, and it ranges from 0 to 10,000. 10,000, of course, would be then a very highly concentrated market and a monopolistic situation in which you have like just one employer in a specific labor market, whereas the labor market it's defined by occupation, region, and time, as I mentioned before. So then we calculate one index for each local occupational labor market throughout the 27 EU countries. This is to give an overview of the R code, which is available on the Eurostat on a repository in the Eurostat GitHub account. So first of all, we query the data from the AWS service for jobs located in all 27 member states, and then we do a little bit of cleaning and filtering of the online job ads. We filter the ads where some variables that we are going to use in the calculation are not available. So for example, geo information, we do not have information on where the job is located, or we do not have information on the type of contract, or for example on the occupation type. Then we eliminate duplicates, so we filter out different online job ads with the same general ID, because it can happen that some job ads that they may have maybe just different in the different source, but then we just keep one job ads with the same general ID. Then there is this part of work which is on consolidating company names. Of course, from the ads extracted from the web, we have this variable which indicates the name of the company, the employer advertising the ads, and this is very important for our calculation, because of course we need to calculate the market shares, so the shares of the hiring market for each company. And we can do this only by using the name of the company. Then we can aggregate the different ads to calculate the shares of which, so how many companies are advertising and what is their share of the market, of the hiring market. Of course, company names, it's quite ill-defined variables because it is scraped and taken from the ads on the web, and then we will see later that we have done some specific work on this, because usually you don't find actually the name of the company that is advertising the job, or maybe you have some other elements instead of a string which represent the name, and we had to clean that. And then we also had to filter out agencies, because sometimes you don't find the name of the company, which is the company that has the actual job opening, but instead you find the name of the recruiting agencies like Manpower or Adecco, to name a few. Then we impute the missing company names. Of course, company names is exposed also to a lot of missings. Then we, for sake of the calculation of the index, we need to impute using some dummy company names to be able then to aggregate and create the share for each specific labor market. Then we have a phase in which we merge the geodata. So we download from Eurostat website using the GISCO package, then the data for Europe, the geodata for Europe, and then also we download the Excel files from the Eurostat website to actually have the names of the functional urban areas and other information like population and geo, other information also on these local administrative units. Also here we had to enter some country exceptions, and I will come back to it later in a moment. Sorry about that. Then we calculate the HHI index. So this is the main part of the code in which for each cell we calculate actually the shares of the market, and then we estimate this index for each local labor market. And here we have tested different alternatives for this calculation that are not relevant for the purpose of today. And finally, we visualize the results, aggregating the results for all the 27 member states, and we prepare output tables and visualizations using ggplot and the GISCO downloaded data for creating the map. So some highlights on what are the main challenges that we have faced using R for this big data processing. So we have had to use and merge different sources. So as mentioned already, from this query to AWS Athena, GISCO information downloaded from via the API in the package, and then also information from Excel files still available on the Eurostat website with information on local administrative units. We had to use base R we chose to use base R functions and data table instead of data frame to improve then memory use and speed of the execution. And then we struggled to find then the optimal package for querying the data from Amazon Web Services. We had to use parallel computation for speeding up the processing of our code, and then we have done some work that I will show later on text processing for company names. And finally, we had some struggles in adjusting geometries for different countries when having to aggregate them for visualization. So I will focus on these last 4 items in bold here in the next few slides. So as I said, the starting data set had over 200 million records. So then after then filtering, eliminated duplicates, this goes down to 100 million. But actually, we have in 12 variables for 27 countries. So you can imagine then the amount of data that we had to process. And regarding the querying from the Athena AWS database, then we started initially with the RJDBC, but then we had to move to R Athena because it was not possible to implement the rotating access token. So the R Athena package was used in a second phase, but finally we had to stick to NOC2A package because of some issues that we found with installing Reticulate and Python, which is what actually substantiates our Athena package. So then this okay. So as you can understand, it was an iterative process. And then regarding the parallelization of computation, we actually parallelize the data retrieval, so the queries by country, and then the calculation of the indicator, and also in a third phase, also the plotting it's parallelized by quarter and country using MCL apply function. So then we struggled a little bit in finding the optimal numbers, of course, then to avoid memory overload. Then we were limited to using max three cores in parallel due to limitation in AWS Athena for concurrent connections. Regarding the text processing, very quickly, so as I mentioned, so it's usually not easy to find then the company name in of the actual company having the opening, but usually maybe you have not the actual employer, but agencies or portals instead of the actual employer. And also you have some problems in that maybe the same employers like IKEA can be written as IKEA or IKEA Sweden or IKEA Sweden AB. So the same actually company might have different strings, might be expressed by different strings. Then we had to actually reconduct and consolidate these names. So when we then encounter something like IKEA Sweden, then we substitute this with just simply IKEA word. And then was done in a first phase using some keywords, as you can see here on the screen. So we actually replace then what we find using grapl and some logical conditions. Then you can find this here in this CSV file that it's manually compiled and then checked after this is run through R to see actually by using these keywords how many company names are filtered out or are consolidated into the, let's say, the original, the true company name. And then we had to, of course, be careful of some exceptions, especially when you have very short company names like ABB or SIDA that may be parts of other longer company names, which are not actually what we are looking for.
Andrea, you should come to the conclusion, please.
Sorry about that. Okay, so text processing for company names. This is just about how we identify the agencies. But I will also very quickly go to also the GISCO challenges. So we had to integrate different type of geometries to make up the final visualization maps. Just to give you an example of the European maps of what this indicator look like. So you can see that the lower concentration index actually appears in the main urban areas in Europe and the bigger urban areas actually, whereas smaller urban areas and in the peripheral of Europe, then you will usually find a higher concentration, which means on average less employers offering jobs in different occupations. So this is an example of the visualization done with ggplot, but then also we have created through the help of colleagues then an interactive map in JavaScript, which is available for scrutiny. And that's it. So future work, we will focus then on improving the cleaning and the classification of company names, calculating the index on a different definition of labor markets. This might change a lot of the conclusions. And then one of the aim that we had was to implement the interactive map, which, as I said, is currently done in JavaScript in R. And of course, then hopefully making this experimental work fit for regular statistical production, and then to see how we can integrate this indicator with current labor market statistics. For further information, if you want to access these old online job ads data set available at Eurostat, you can drop your inquiries to this email, estat-waih.ac Europa EU. Then you will have to specify which project you want to work on, and maybe you can be granted access to the dataset. Code is available on GitHub, and we will publish a statistical working paper soon in early December 2021. So sorry for being a little bit over time. This was my presentation, and if you have questions, we will be happy to answer.
Thank you, Andrea, for the presentation. I would actually move on right to the next presentation, because we have 2 more presentations before we should go to lunch. And I don't see a question right now in the chat. So if you have questions, please contact Andrea directly afterwards, for example, via the chat. So moving on to the next presentation. I think Shirley is presenting, if I'm not mistaken, because I saw her, or is Rui Alves presenting?
Yes, good morning, it's me.
Okay, you are presenting, perfect. So Rui Alves from Statistics Portugal will present network visualization of multi-data sources using R. And you're already sharing the screen, we can see that fine, so please go ahead.
Thank you, Alexander. Good morning, everyone. It's great to be here. We're going to make a presentation on network visualization of multi-data sources using R. Both the script and the rendered result in HTML format are available for download in the link to the GitHub account you have on your screen. If you'd like, you can download and run it on your RStudio or open the HTML file in any browser. And now Christina is going to give you the context in which this network visualization of multi-data sources emerged. Christina, the floor is yours.
Thank you very much, Rui. Good morning to everyone. Well, SNet Big Data 2 was a project within the European Statistical System, jointly undertaken by 28 partners, which was run from November 2018 until December 2020. Its objective was the integration of big data in the regular production of official statistics through pilots exploring the potential of selected big data sources and through building and implementing concrete applications. It was a continuation of SNet Big Data 1 and consists of 12 work packages. One of them was work package J, Innovative Turing Statistics. The main objective of this package was to address the need of a conceptual framework and setting up a smart pilot tourism information system that will support statistical production in the field of tourism by integrating various big data sources with administrative registers and statistical database using innovative statistical methods in order to address data discrepancies, incoherent concepts, indirect relations between sources, redundancies of information. The use of new information sources, including big data sources, in official statistics opens up completely new possibilities of enriching and improving the system of tourist statistics. Thanks to external sources of information, the data provided by official statistics can be more current and reflect the user needs. Now Shirley is going to explain why do we need a network tool. Thank you very much.
We cannot see anything at the moment. So maybe you have to unmute yourself.
Can you hear me?
Now we can hear you, yes.
Can you hear me?
Yeah.
Sorry, I'm not. Official statistics rely strongly on changes on it.
No, you are out again. Not sure. Maybe one of your colleagues could also present this part.
Yes, can you not hear me?
Hardly.
Okay, that is maybe Rui. Can you take it over?
Yes, of course, Shirley. So Why do you need a network tool? Official statistics rely strongly on monitoring properly and timely changes on economic activities. Economic activities can often cross territorial borders as well knowledge fields. Tourism statistics is one of this kind because hospitality industry requires and incorporates information on various fields like hotels and accommodations, but also catering, housing and building markets, cultural, sports, etc. Surveys and registers are commonly used to produce official statistics. However, it is also known that the majority of tourist accommodations is booked online. That also for large leisure activities or events. This sort of big data is becoming an important source of information for NSIs. Hence, getting a rapid overview and intelligence of the data sources type, data sources used and outputs produced by other NSIs are of crucial importance. Ideally, one should be able to trace back and forth the data sources and statistical output, which means identifying and visualizing which countries use the same or similar sources, understanding the purpose of the use of a specific source, being capable to browse directly into external sources and get news insight. All these stages have the target of supporting statistical production process in a way that potential efficiency gains can be accessed. The starting point of the WPJ was developing an inventory of current and potential data sources that can or could be used to produce fast and reliable statistic output. A multiple number of individual workflows was collected. On this slide, you can see that the heterogeneity across the country workflows is large. Workflows are schemes or models showing the input and output of NSI's statistical process to produce, for example, tourism statistics. You can notice that it was not easy to get a full picture. So the solution was an interactive network visualization. From a user point of view, the solution to this problem was develop an interactive network visualization, which has two main selection criteria: a single node, here in this combo box, and the group or topic. As you can observe, important nodes are placed in the center. The green dots represent data sources types, the orange dots represent data sources, and the purple squares stand for outputs. Notice that the bigger the nodes, the bigger the nodes relate to more countries. For instance, here, this node improve quality of satellite accounts. We have 7 countries, I guess. But if you go to a smaller node, you can see that it is only related to one country. On the bottom, we have green buttons on the left and on the right that help you to navigate and zoom in, zoom out, or recenter the network. You can refresh the page in the browser, which rebuilds the network, and you can pull any node that the network will rearrange, the layout will rearrange itself automatically. So by dragging a center node, you can see that it has a huge importance in the whole network. But if you drag a peripheral node, you see that the impact is, well, much lesser. Further, by hovering the mouse over a node enables you to show additional information. This is important because if we use labels, very long labels, the network will be cluttered with text. Further, to visit an external link, which is this triangular shapes nodes, these external links can be either HTML files, PDFs, image, Excel files, etc. So if I just click here, I go to an external node. Yeah, this is it. So in this case, it's an HTML page. It's from hotels.com, but it could be any document in your local network of your work, for instance. You can also do a multi-selection by using control-click. And if you want to freeze a specific layout, for example, if I just select here and here, and this one over here. If I want to freeze this layout, I would use this button here on the bottom, export as PNG, and it will export an external file. So now let's say you want to know the importance of web scrape data. So let us choose the group data source web scrape data. We can see which sources were scraped, namely hotels, Booking, TripAdvisor, and Airbnb. Notice that the bigger node, the more countries are involved using this data. If you wonder how many countries use Booking, well, just hover over the node, and you will see that there are 6 countries collecting Booking.com data. To what results? You may guess the purpose of using this data in terms of official statistics. I mean, improving the accommodation inventory, but also to learn more about aggregated information of visitors on expenditures levels and visited areas. Look at the colors of the lines. They show the predominant connection of a node. Let us now select the node in this first combo block. Quality of the tourist expenses data. Notice again, the bigger the node, the more countries involved using this data. We observe that 6 out of 8 countries have a survey on participation of residents in trips, and also 6 countries have a survey on tourism accommodation base. 2 countries used airport registers and, as shown before, also web scrape data from hotels, Booking, and other booking websites. In short, using this VIS network tool, we can see back and forth the data sources and the data types involved. Besides, we can also read out that there are 2 other outputs connected to expenditures, namely improve the survey data on trips and improving the quality of satellite accounts. Now, how does this work? Without wanting to turn this presentation into a tutorial, we'd like to share with you how we did this. The first step required a significant work of reconceptualization in order to make the different workflows compatible and consistent, without tampering with their substance. The majority of the countries used a similar template, but its implementations and content varied slightly. So making everything compatible was quite challenging. The first thing to do is, at least in this particular case, was to translate the static workflows, sorry about this, the static workflows into 2 tables or data frames that are nodes and edges. These are the core of the network. Nodes data frame has a numeric ID of the nodes and their properties such as size, shape, and color. It also has label and title, which provide the tooltip information when hovering over a node, and group that have the data for the combo boxes. The edges table or data frame has information on the connections and also on the length, width, and arrow type. The IDs for the from and to are the same as the nodes IDs. The next thing was to create a script to produce a dynamic and interactive network. From several available options, we used the VIS network package, an R interface to vis.js JavaScript library. And although it's not mandatory to know about JavaScript to use this package, some basic knowledge is helpful for things such as action-related events. The VIS network package is very flexible and accessible, not only because it's based upon open source software, but also because it works on any modern browser up to a few thousand nodes and edges. It is based on HTML widgets, so it's quite compatible with Shiny, R Markdown documents, and RStudio Viewer. The script, which can be downloaded from the GitHub account, is self-contained in the sense that the data is embedded. There's no need to load or import data, just run the script. Just running the script will produce the data frames. You can do this by using the DUftA base R command to recreate the data frame. So if you are in a RStudio session and you have a data frame and you want to translate it into code, you just use this command, DUftA, and you will have in your console the code that will generate the precise data frame. So the script is also commented, which may be useful to understand what the script is doing if you want to change parameters. And this is important for us because we really want to encourage everyone to try this or with other data. And so we made an effort to make this as easy as possible. The script is also organized in a layout format, useful to navigate through the code. And to show this document outline, you can either use Ctrl-Shift-O or just click that button on the top right corner of your RStudio window. Now I'd like to share with you this very useful command, visconfigure, visnetwork editor, that lets you to configure and view options directly and immediately on your network, and without writing a single line of code or going through that tedious process of changing one parameter at a time on the script, run the whole thing, and then finally observe the result in the viewer window. So this is our network. And here on the bottom left, you have all these parameters. Let's go to the physics section. And you just experiment with these slide bars or with these checkboxes, and you have an immediate result in your network. So you just can tweak the parameters in an interactive way, and then just use the results. You can use even this button to generate the code, and to copy and paste them to your final script. So these are the citations for the package mentioned in this presentation. dplyr, well, I always end up using it, so it might as well be in the first place. Visnetwork, which is what makes the heavy work in this case. RStudio API, which is needed for the set_wd function that we use on our script. And Shiny, if you want to run the visnetwork editor command. And that's it for me, and thank you for your attention.
Thank you very much. And sorry about the technical problems we had during the presentation. I would move on again because we only have 10 minutes left for the last presentation. And the last presenter should, of course, also have his full 50 minutes to present. With that, the next presenter is Stefano Gualandi from the University of Pavia. And I see the screen is already shared, so please go ahead.
Okay, thanks a lot for the invitation to present in this conference about air. I'm going to present our joint work with Federico Bassetti from Politecnico di Milano and Fabio Ricciardio, that is also online. And I would also like to thank Matthias Mezaros, because he really gave a big hand at the beginning of this work. So the outline of the talk is as follows. Before I'm going to present the type of problem that you aim to resolve with the air package that I'm going to present, then I will briefly present small example of the use of the package, and I will show some computational results using the data, spatial data from the whole region of Belgium, to show how the package scale with the size of the data, and so how large we can go with the data. Proto, it's okay?
I just heard also something, but I'm not sure where it came from. I will look for it.
Okay, I can go forward then. So I hear you very well, Alexander, so you can stop me at any time. Okay, so let's start with a really toy example in one dimension, and then we scale up with dimension, and we go to the point. So let me start with a very basic example, an academic example. So suppose we have two normal distribution, empirical distribution, so we have n samples, and we want to compare. Let's say we have a blue distribution and a red distribution, and then we want to somehow measure how the two distributions are similar. So we can think that we have a fixed distribution, that is the blue one, and then we have the red distribution, and we start to change the mean of the red distribution as long in such a way that we really have, we start to have two distributions that start to be different. At this point, we want to compare the two distributions. We want to see how they are similar. At this point, we have two strategic options. Either we use a divergence of a similarity measure that is based only on each single being height. And so, for instance, we can use the L2 norm, and we see that as long as the two distributions start to be far away, so start to be different, we have that at the beginning, the L2 norm grow, and then at a certain point is saturated. It's no longer able to capture the notion of difference between the two distributions. On the other side, we have some cross-bin notion of divergence of measure that are able to continue to capture the difference between the two data sets, the two distribution, also when the two sample distribution are not longer overlapping. So this is a key notion. So if we want to compare two histograms, we have two possibilities. Either we use a notion of measure, or discriminative measure, or similarity measure, that is based only on the comparison between bin to bin, or we move to a cross-bin dissimilarity measure that usually go in a quadratic form, so are more demanding computational, but can be more precise when the two histograms have a strong notion of spatiality. I mean, they have a geometry behind. Intuitively, what we have is we want a notion like the earth mover distance, that is an example of cross-bin similarity measure, where we are comparing more horizontally to distribution and not only vertically. And this is the first point. There is a second point that is crucial to compare between bin to bin and cross-bin distribution, is that we do not want to be sensible to the size of the bin, because if we just take a notion of distance that take only the bins, depending on how large is the bin, we can have a different measure of distance. While if we take a cross-bin distance, if we take a cross-bin distance, we are robust to the size of the bins. So this is what's happening in one dimension. The title of the talk is about spatial map. Indeed, we are interested more on histograms that came on the plane that are in 2 dimensions. And the big difference is that, okay, we want to use the earth mover distance, that is also known as the Kantorovich passes distance. And the point is that going from 1 dimension to 2 dimension computationally is really a big step, because in 1 dimension we can compute the distance in times n log n, but when we move from 1 dimension to 2 dimension, the computationally we really have a big overhead. So in this talk, the key point is that we want to propose an efficient R package that is based on a Kantorovich passes and distance to compare spatial maps. And we do have an efficient implementation. That implementation is in C++, but we provide a user-friendly R wrapper that can be used to compare large spatial maps. I go very fast on the optimization side, where is more my expertise. I say before that to compute the earth mover distance, we have to solve a complex optimization problem. And we can imagine that if we have 2 distributions with n bins in the support of the distribution, the complexity of the problem goes like n to the power of 4. So there is little hope that we can scale up to large distances. It's because to compute the distance, it's not like the Euclidean distance that we can compute the distance in a linear time. So what we have done in academic work, we have proposed a really efficient method to approximate the distance. So we trade off a bit of accuracy on the optimal solution of the optimization problem. We don't really are interested in the very exact optimal solution, but we accept a small error that is a function of an index. It is what we call a coprime index. And this coprime index is going to impact how is big the real network that we are going to use to solve the optimization problem. And I not go into the details, but this table is quite important to understand the impact of parameter L, is that as if we fix, for instance, a value of 3 for the parameter L, what we call the coprime index, then we can prove mathematically that we do not commit an error larger than 1.29% of the optimum. And this is a worst case error. In practice, we get really smaller error. And so by playing with this parameter, we can decide how much we want to precise and how much we can be efficient in solving large distances. So how we can use this idea? where we have developed an R package that is called a SpaceTVD. And the desiderata for this package is to be able to solve an application, from an application perspective, a problem like this one. Suppose we have a true distribution, and we try to estimate where the distribution, this empirical distribution came from. So we can try different model, different estimate of the distribution, and then we can compare each of the estimates that we have at hand with the empirical distribution. And we can use this notion of distance to find the estimate that has the smaller distance. So somehow we are trying to estimate the empirical distribution with a theoretical estimate. So there will be this afternoon an afternoon session, more detail on this application, talks given by Marco Ramelajak. And this is somehow motivating the package. And in the R package, we expose only 4 functions. So we hide somehow all the algorithmic complexity in a C++ implementation. And then in R, we expose these 4 functions. That is compare 1 to 1 if we want to compare a couple of spatial maps. If we have one reference in spatial map that has to compare with a number, return the complete matrix of distances between all the pairwise measure. And then finally, there's a question in the chat. I will take it later. And finally, we have a focus area that permits not to compare the whole region, but just to focus on a small region and to find somehow the smallest region that best match another spatial map. So how we can use the library? So the library is available on Crown. So we have to install the library, and then we import the library. We have to define which are the set of support points of the true distribution. Here, just taking like 90 points that are uniform distributed on a square of size 31 by 31, and we build a matrix of coordinates. Then suppose we want to compare 4 different spatial maps. Here again, for simplicity, I'm not here interested in the application, but just to show how to use the package, we can draw 4 random, 4 uniform distribution on the same size, and then we can, once we have built the coordinates and the weights, we can call one of the functions that I showed you before, for example, the compare all, by passing input the data, by setting the copri index L, and this is very important, and then we get back either the distance of a single couple or the whole matrix. In this case, we are calling compare all, and so what we really are getting as a distance is a symmetric distance where we have all the pairwise distances. And we have a number of parameters on the function of compare all, so they are all set to the default value. And indeed, the coprime index is the most important because somehow impact how precise we are in computing the exact solution. There are other 2 parameters that are important. One is the convex hull parameter, because if we are dealing with a spatial map, as for instance the region of Belgium, we don't really have a square histograms. We have a regular map, and we might be interested in taking the convex hull of the region, and in that case, we have to define what is the true distance between 2 points within the region. If we want to cross border, or if we want a line of sight distance. And this is the first point. And the second point is another very important parameter, is for the focus area function, that we can decide if our focus area is either circular or square. And once we have a focus area, from a mathematical point of view, we no longer have a balanced Hotman transport problem. I mean, the concept of distance is really mathematically different, but we have a number of options to configure the solver to deal with all the different possibilities. And for the computational evaluation, we try to use to derive some synthetic data starting from data that are released from StatBel, that is the official statistic institute for Belgium. And what we did is we take the whole Belgium, we take a different tile resolution, so the number of nodes correspond to the number of tiles of the region discretized like 1 kilometer by 1 kilometer, and we look at the runtime, and here each row is the average over a large number of instances, and we see that as we try to get a big map that is smallest resolution, we make grow a lot the number of tiles of our map, the computational time goes up, but still 500 seconds is like a few minutes. So it depends on the application. It's not really something like online. We can really solve also very precise data. Indeed, there is not only the size of the map that has an impact, there is also the coprime index. And I show you before that we have a worst case bound on the optimal solution, but in practice, already when we have L equal 3, we already are quite close to the optimum. So we can save runtime by taking not too much too large value for the coprime index L, but still have something like a very good estimate of the optimal solution. And what came out as a surprise somehow from our project that we try to compare the runtime both from a cluster and a desktop computer, and somehow the desktop is faster. So it took a while to understand why the desktop was faster. The point is that the cluster was is configured to be green, I mean energy friendly, so it never go to the maximum clock power. But you can see that a normal desktop we are able to solve quite reasonable in very fast time in some very large cases. And I forgot to start the time at the beginning.
We're at about 50 minutes now, so
so I have the last slide and then I conclude. Thanks, Alexander. So, and there is I try to present the package really as an application dependent, but we really invite you to follow this afternoon the talk by Marco Lamjak, because he has a very nice notebook where he has used our package for a concrete application, where they also have the paper online. And then, so if you want to play with the package, we have all the source code is available on the Eurostat GitHub repository, so you can find also the C++ code and everything. You have indeed a wrapper, and we also have a Python wrapper. And the documentation of the wrapper is, I mean, I think I hope is useful. That's it. So that's all for me. If you have any question, I saw a couple of questions in the chat. I can try to answer, but you have to give me the time to read the chat.
Thank you very much for the nice presentation and the great new package. Actually, there are two questions, but I think Fabio answered both of them. So the first one is, can you also use the spatial KWD package on raster objects?
Which kind of object?
Raster objects. So I guess, I mean, it's working on grid data, so it should be working also on raster objects. That's an R object class that exists.
Fabio, have you got the question?
Stefano, can you hear me?
Yes.
Yeah, this is Marco. Thank you for all the credits. I don't think there is a direct implementation for raster objects, but you can actually just transform. So this is the same what I do as well. I use them on raster or SF objects, and I just transform them so the package can work with it. So this is no problem. There's just a transformation involved.
Okay, thanks again, Marco. Likely you are here.
And maybe the other question is, are the computational complexity and load reduced when considering only discrete distributions, and by how much?
Okay, the theoretical complexity of the algorithm is awful. It's horrible because it's like n cube log n. But the point is that algorithmic, from an algorithmic perspective, I jumped these parts, but we really make a big effort to be as lazy as possible in the computation and to have as small as possible memory footprint. We really go to look at the cache misses in memory, and at the end we try to make like an empirical estimation of the theoretical complexity, and it looks like he goes a bit more than n square. It is between n square and n square log n. That indeed is much more than the linear complexity of an Euclidean distance, but the overall time on a region as Belgium is I think is if you are not to be on real time, is acceptable. So the worst case complexity is n cubed log n, the empirical complexity is n square log n. In practice, I mean, it's a matter of few minutes for the Belgium region at a resolution of 500 meters.
Okay, that does not sound too bad, yeah. Thank you. Thank you again for the presentation. We are already late for our lunch. And with that, I conclude this session and hope to see all of you again at 1 o'clock for the session on dissemination and visualization. Enjoy a lunch break. See you later.